The next skill that we need to master is being able to create a truth table from a digital logic circuit. Now, it turns out that there are actually 3 equivalent ways of representing information about a digital function. We can either have the complete digital circuit diagram, which is really what we've been accustomed to in the past, or as we've just seen, we can have a Boolean function that specifies the output as a function of the inputs. Those two are completely equivalent to each other. If I have one, I can generate the other. And so we don't need to keep track of both of them. If we go from the circuit diagram to the Boolean function, we can almost set the circuit diagram aside and then really just focus our attention on the Boolean function. The third one, though, that we really haven't talked about is a truth table. And a truth table, we've seen truth tables before. There's a row for every possible combination of the inputs, and it shows what the output is going to be. And so it's sort of like if you ask the jury, what is your verdict? And they would say, well, we're going to give it to you on paper. That would be the complete digital circuit diagram. Or we're going to tell you what our vote was. It was 10-2. Or we're going to poll the jurors and we're going to say, what was your vote? What was your vote? What was your vote? And all 3 of those are really going to be equivalent to each other. So we need to be able to construct a truth table. One thing to observe is that if you have a circuit or a function with n inputs, then the truth table will have 2 to the n rows. So that means that the truth table grows very quickly as you have an increasing number of inputs. We're most accustomed to digital functions that have 2 or 3 or 4 inputs. Once you get beyond 16 rows, it gets to really be difficult, sort of tedious to write the truth table. So we'll tend to use other methods after that. So we're really going to focus on 2 inputs, which has 4 rows, 3 inputs, which has 8 rows, or 4 inputs that have 16 rows. Now, there are 3 approaches to creating the truth table. One is great, one is very, very clever, one of them is okay, and the other one is terrible. And so I'm going to tell you about the terrible one first so you appreciate the other 2. The terrible one is tedious. Perform the ones and zeros analysis from section 1, what we call the literal digital logic function analysis, for every possible combination of inputs. So you would follow one of those examples and you would do it 4 or 8 or 16 times with all the different possible combinations of ones and zeros. Now that is going to be a bad decision. I do not recommend it. I don't recommend it on homework. I don't recommend it on in-class exercises. I don't recommend it on exams. I most especially don't recommend it on exams. The only reason why I tell you about this method is because you might have thought of it and because I want you to really appreciate the other 2 methods. Now, the second method we actually already saw when we talked about perfect induction, and that is to create columns for each intermediate result and then finish with a column for the output of the whole circuit. Now, that's really not the one that I want to focus on, but that would be a reasonable way to approach creating the truth table. So if you had a complex function, let's imagine if you have a complex function like this one, I could create a column that is not A and B. I could create a column that is A and not B, and then I could have an extra column which is going to be not A and B ORed with A and not B. It's a reasonable way to approach it, but it's a lot more work than you have to do. The best method, my preferred method, is to first write the Boolean equation as outlined in the previous section. So if you're given the circuit diagram, you have to write the Boolean equation first. Then you have to rearrange the equation, if necessary, so that it's in what's called sum of products form, or SOP form. Sum of products means that it is a series of OR functions combining terms that each contain only AND functions. So an example, as I was pointing to this function earlier, this is an example of SOP form. So you can see here that this term right here, not A and B, well, that's a product. That's an AND. I'm ANDing not A with B. The not part is not a concern. We can have the not or we can not have the not. And then I'm going to OR it with another term that is just an AND, A and not B. So when you have something that it has the groups contain only ANDs, and those groups are only ORed together, that's sum of products form. And if your function comes in sum of products form, great. Then you're ready to immediately apply the shortcut to create the truth table. But if not, here's an example from figure 3, for example. This is definitely not in sum of products form. For one thing, it's got inside the parentheses, it has an OR. Outside the parentheses, it has an AND. There's a bar across the whole thing. That bar across individual variables is fine, but across the whole thing is not fine. So let's apply De Morgan's theorem once. So you can see here that I've broken the bar into 2 pieces. I've replaced the AND with an OR. Let's go ahead and apply De Morgan's theorem a second time for this first term. I replaced the long bar with 2 shorter bars, and I replaced the OR with an AND. And now what I have is an expression that is in sum of products form. It's a product ORed with another product. Well, it's not really a product, it's just a variable, but it's fine. You don't have to have a product there. You don't even have to have the or. If I just had not A and not B, that would still be sum of products form, because you don't have to take full advantage of everything that's available. You just can't have anything that's not allowed. So this is now in sum of products form. That means that I can quickly and easily fill in the truth table. So once your function is in SOP form, you can quickly fill in the truth table by remembering that variables that appear without a bar must be 1, and variables that appear with a bar must be 0. So for example, let's consider figure 5, where we're going to build the truth table for the function A and not B. Now that's also in sum of products form. It just happens to be that it's a product. And it doesn't really being summed with anything else, but that's fine. You don't have to sum it with anything else. It's like the simplest sum of products function that you can get. So A and not B. A is not complemented, so it must be a 1. B is complemented, so it must be a 0. And those must happen at the same time. So if I come down here in the truth table and I look for places where A is 1 and B is 0, well, that would be this third row right here. So I'm going to go ahead and fill in the 1 right here, and that 1 is coming directly from the A and not B. Now that's the only row that satisfies the requirements, and therefore all the other rows are going to be 0. So the first row, the second row, and the fourth row all contain a 0. The way that this method works is you fill in the 1s, and whatever didn't get a 1 is automatically going to get a 0. So let's look at another example. Here I have not A and not B, or not C. That's the one that we just converted using De Morgan's theorem. Now the not A and not B, that means that A has to be 0 and B has to be 0, and I don't care about C. So you can see that here in this first row, A is 0 and B is 0. Don't care about C, so that one gets a 1. And I've made a note here to the side that this came from the not A and not B term. Here A is 0 and B is 0. Don't care about the 1, so that gets a 1, and it's also from the not A and not B term. Those are the only two places where A and B are both 0 in the whole truth table. Let's consider now that it's OR. So it can either come a 1 from the first term or from the second term, or if there's a third or a fourth or a fifth term. But in this case, there's only 2 terms. So I've already counted the 2 rows that became 1 from the not A and not B. Now let's look at the not C. So not C, well, here's 1. Hey, that row's already been covered by not A and not B, but that's no problem. It's just double covered. It is absolutely positively going to be a 1. Here's another place where C is equal to 0. Not C, C bar means that C has to be 0, and I don't care about what A and B contain. So that gets a 1. And this note, out here to the side, I'm just saying to myself, hey, showing my work, how did I get that that was a 1? I got that that was a 1 because I think that it's covered by the C bar. Here's one where C is 0, so I put a 1, and that's covered by the C bar. This C is a 0, so it becomes a 1, and therefore that's covered by the C bar. That's everything that has C equals 0, and it's everything that has not A and not B. So all the remaining elements, this one, and this one, all now get a 0, and the truth table is complete. So there were 2 terms that were separated by an OR function, so we had to account for each of those 2 terms. And if a particular row in the truth table is covered by either or both, then it's going to be a 1. So that means that now you have enough information to solve the constructing truth tables example problem. Watch the video, make sure that you understood how it worked, then come back and we'll talk about simplification.